Now we are going to see an example about sizing a PFR. The reaction described by the data in table 2.3 is to be carried out in a PFR. The entering molar flow rate of A is 0.4 moles per second. A. Use one of the integration formulas given in the appendix A4 of the book to determine the PFR reactor volume necessary to achieve 80% conversion. B. Shade the area in figure 2.2 that will give the PFR volume necessary to achieve 80% conversion. And C. Make a qualitative sketch of the conversion X and the rate of reaction minus RA down the length of the reactor. Solution. We start by using the table 2.3. So we have in this table two rows. In the first row we will have the conversion X, and in the second row we have FA0 divided by minus RA in cubic meters. So A. For the PFR, the differential form of the mole balance is FA0 dx in dB is equal to minus RA. Rearranging and integrating will give us that B is equal to FA0, the integral of dx divided by minus RA, and we put FA0 inside of the integral to have the relation FA0 divided by minus RA, so we will have the integral of FA0 divided by minus RA times dx with the limit from 0 to 0.8. We shall use the 5-point quadrature formula A23 given in the appendix A4 to numerically evaluate the above equation. The 5-point formula with a final conversion of 0.8 gives 4 equal segments between x equals 0 and x equals 0.8, with a segment length delta x equal to 0.8 divided by 4, which is 0.2. The function inside the integral is evaluated at x equals 0, x equals 0.2, x equals 0.4, x equals 0.6, and x equals 0.8. We must note it here that we need to take the points in which the difference is the same. That means that we don't take point number 2, which is the conversion 0.1, and the conversion 0.7, because delta there is not 0.2. So the formula is that the volume is delta x divided by 3 times FA0 divided by minus RA at x equals 0 plus 4 times FA0 divided by minus RA at x equals 0.2 plus 2 times FA0 divided by minus RA at x equals 0.4 plus 4 FA0 divided by minus RA at x equals 0.6 plus FA0 divided by minus RA at x equals 0.8. If we use the values for FA0 divided by minus RA given in table 2.3, we will have that the volume will be 0.2 divided by 3 times 0.89 plus 4 times 1.33 plus 2 times 2.05 plus 4 times 3.54 plus 8. That will give us a total volume of 2,165 liters. The PFR reactor volume necessary to achieve 80% conversion is 2,165 liters. This volume could result from a bank of 100 PFR that are each 0.1 meters in diameter with a length of 2.8 meters. If we recall the problem number 1 and number 2, we resolve the same problem that we are facing now, but for a CSTR, and we got a result of 6,400 liters. But here, with a PFR, we only use 2,165 liters. B. The integral in the question defining the volume can also be evaluated from the area under the curve of a plot of FA0 divided by minus RA versus X. So the volume is equal to the integral of FA0 divided by minus RA times dx with limit from 0 to 0.8. And the area under the curve between x equals 0 and x equals 0.8 is in the figure at the bottom of this page. And this area corresponds to 2,165 liters. And this plot is the Levenspiel plot for a PFR. C. Sketch the profiles of minus RA and X down the length of the reactor. Solution. We know that as we proceed down the reactor and more of the reactant is consumed, the concentration of reactants decreases as does the rate of disappearance of A. Remember that the rate is directly proportional to the concentration, so if the concentration decreases, so does the rate. However, the conversion increases as more and more reactant is converted to product. For x equals 0.2, we calculate the corresponding reactor volume using Simpson's rules given in the appendix A4, equation A21 of your book, with delta x equals 0.1 and the data in table 2.3. So here we are going to take 3 points, x equals 0, x equals 0.1, and x equals 0.2. And as you can notice, the difference is only 0.1 from 0 to 0.1, and from 0.1 to 0.2, the increase is only 0.1, so delta x is equal 0.1. So the volume will be 0.1 divided by 3 times 0.89 plus 4 times 1.08 plus 1.33, which will give us a volume of 218 liters. So, as we can see here, if we only require a conversion of 0.2 in this reaction, we will need a very small reactor of 218 liters. But what about if we want a conversion of 0.4? We will use again this Simpson rule, but now with a delta X of 0.2 to find the reactor volume necessary for a conversion of 40%. And here we are going to take the points of conversion X equals 0.0, 0.2, and 0.4 because that's the limit that we want to achieve. That's the conversion we want to achieve. Remember, we don't take 0.1 because we need the delta to be the same. So the volume in this case will be delta X divided by 3 times FA0 divided by minus RA evaluated at X equals 0 plus 4 times FA0 divided by minus RA at X equals 0.2 plus FA0 divided by minus RA at X equals 0.4. And if we substitute in this equation the values given in the table, we will have that the volume will be 0.2 divided by 3 times 0.89 plus 4 times 1.33 plus 2.05, which will give us 551 liters or 0.551 cubic meters. If we continue in this manner, we will get the table E231, which is down here, for different conversions. And by example, if for a conversion of 0.6, we will need a reactor with a volume of 1,093 liters, and for a conversion of 0.8, we will need a reactor of 2,165 liters, which was the volume that we obtained initially in this problem. And here we have the plots of conversion against volume. So we see that at conversion 0, we need 0 volume of the reactor, and at conversion 0.8, we will need 2,165 liters of volume. On the other hand, the plot to the right is the value of the rate. And as we can see here, at volume 0 of the reactor, we have the maximum rate. And this rate decreases as we move throughout the reactor until we reach the value of the volume 2,165, and here we have the minimum rate